Hello, everyone. Welcome to the fourth talk of this series of conferences and organized by the Virtual Learning University for young researcher and also PhD student. Many thanks to Professor Ahmed Ennaoui, founder of the Virtual Learning University, for organizing this series of seminars. And also many thanks to Ustad Salim Omar from Physique for education and training for the Zoom platform for this series of seminars. First, I give the floor to Professor Ahmed Ennaoui for an introduction to this talk of today. You have the floor, Professor Ahmed.
Thank you very much. So let me first make the screen. Okay, so I think my screen is visible, I guess. Okay, so I will, you see my screen, isn't?
Yeah.
Okay, thank you very much. So I want to always remember for the students some very fundamental issue which are very important for the to understand the topic. And what you see here is a semiconductor, what I show here in the left. It's a flat band semiconductor. And in front of it, I just represent an electrolyte. And I represent an electrolyte like a solid with a redox system. And the red color, this means is full of electron, and the other one is empty. So the red and the ox. And of course, it's in the energy vertically, that is energy scale. Okay, so this means here in this axis here, it will be the energy. Okay, and here is before contact. And here after the contact at equilibrium. And I represent, of course, the vacuum level here. I will extend this axis. Sorry for the inconvenience that the axis is not very vertical. So this is 0 here. That's the vacuum. And of course, the band are banded here after contact, because the semiconductor lost electron, which go to the electrolyte. And you have a band bending. And I represent here the electronic affinity, the band gap of the semiconductor. And this region here will be the exchange between the electrolyte and the semiconductor. That's the way a physicist try to understand the phenomena. And of course, there is a relationship between chemistry and physics. And this kind of relationship, the chemists know it very well, the electrochemical potential, which is equal chemical potential plus the Faraday multiplied by this quantity here. And you can see this for every species with this relationship where you have the concentration of your of the species in the electrolyte here. So this is a background. Maybe sometime we can go back to this background to understand. Okay. Now let's look just this semiconductor when it's there is a contact and it's illuminated. I show you here a very favorable situation where you have the levels of redox, the water, where the water will be oxidized and reduced, and the difference is 2-3 electron volt. This we explained many times, and I show you here. It's a electrolyzers or a electrochemical cell with 2 electrodes. One is the semiconductor in the right, and the other one is the metal in the left. And I show you here a valence band here with D character. This means it's a semiconductor where, if you look to these pieces of the Mendeleev table, maybe it's a material with iron or cobalt or nickel in combination with oxygen maybe, or chalcogyne, etc. That's why we have a valence band where there is a D character. When you put together oxygen with a metal like iron, for example, you can have iron oxide, and then you have a semiconductor Fe2O3, for example, which has a D character in the valence band. This is very important to notice. I show you here the evolution reaction for oxygen, which exchange 4 proton, 4 holes, and the evolution reaction for hydrogen also is a multi-electron exchange. So that's how it is. And what is here activated here is the catalyst. I just want to show you that whatever you want to do when you want to produce hydrogen, you need a catalyst. Either your material is a semiconductor, have a semiconductor property and catalytic properties, or you have to add and in the interface a catalyst. So this is just to remember you. I have also to remember that there is a electrochemical scale and there is solid state scale. And the red one is electrochemical scale, where I just put here the hydrogen. It's as a reference. I just here in the is a little bit negative, 0.16 or 18 volt. You have a silver saturated electrode, which you can use instead of hydrogen. So I put here also the schematic of hydrogen, but in the practice, we use rather very other electrode like calomel or silver chloride saturated here, as you see here. And then I put also some redox system like iron 2+, iron 3+, 2+, iodine minus, iodine 2, chlorine here. So I tried to make it in the right position here. Okay, so you have to keep in mind now that there are 2 scales, and you can find the relationship between the scale of the solid state scale, the scale of physicist, and the scale of electrochemist. And there is a relationship which give you this the relation between the 2 scale here. There is a something like minus 4.5 electron volt. This means here in this level here you have in front of the electrochemical scale you have minus 4.5 electron volt. Okay, so all this as background what you have to know. I show you also here a very important schematic here where when the semiconductor is illuminated, you're in the region where the light is penetrating, and the light is penetrating until 1 over alpha. This means alpha minus 1. All this is all equilibrium, and therefore you have to deal with quasi-Fermi level. What I show you here, there is a quasi-Fermi level for electron and quasi-niveau Fermi for holes. And there is the relationship which differ from the equilibrium by this excess of holes and the electron where the semiconductor is illuminated. It's all these schematic are very important, and we will repeat it again and again until you understand what's going on. Now, what I want to show you some slides which show you what we can do in the lab. Here you see an electrochemical cell with 3 electrodes. One is the counter electrode. It's always we use carbon electrode as counter electrode. There is a reference electrode, like I show you. We can use silver electrode or calomel, you see here, and we can do a very important experiment with this kind of setup, because every electrochemical device has to be very well studied qualitatively and quantitatively. And you know, when you have either you illuminate your semiconductor, for example, your working electrode is a semiconductor, for example, here. Like I showed you before, you have a semiconductor with the band bending here when it's contact with electrolyte, and your Fermi level here, or you apply a potential. There are electron transfer, there are mass transfer, and there is a lot happen in the electrode-electrolyte interface. So complex process can happen: absorption of on the electrode, dissolution, nucleation of reactant and product, charge transfer between electrolyte and the electrode. And this has to be studied with this kind of setup, what you see here. And you need what we call a potentiostat. Potentiostat is just a system where you can control the potential. When you give a potential between working electrode and the reference electrode, as you see here, when you give a potential here, what I show you here in this cyclic voltammetry here, you have a potential which is proportional to the time. You can drive a IV characteristic, and this kind of characteristic, you will scan the potential. This means your Fermi level of your either a semiconductor or a metal will go through different value of the potential. And then if you are in the favorable position to make an oxidation or reduction, you can see this in the characteristic. And that's very important issue that the student know how to manipulate the potentiostat in order to know which reaction happened in which potential, in order to make the analogy with the theory when you are doing some calculation. Okay. Of course, you can use other method, which is known like X-ray photoelectron spectroscopy, where you can even make in situ sometime. You can have, for example, your electrode after making a potential, you apply a potential, you know exactly that in this potential what's happened. You can analyze your electrode under vacuum and see what you have produced on the electrode, or what you have absorbed on the electrode, or if you have deposited something on your electrode. For example, if you are starting batteries, you don't want to deposit, you want to intercalate inside your electrode, and you can learn about this process. That's one thing. Another thing, when you are studying the semiconductors, you can know what we call flat band potential. This means when the potential where it gives you flat band position. This means your band are flat. This also you can know it by using by superposing to your potentiostat in addition to this potential small perturbation here, a small perturbation sinusoidal. Actually, the potentiostat contain a generator for this sinusoidal wave, but you can also buy what we call lock-in amplifier to which is outside your potentiostat to analyze your response and to measure your capacitance. The sample way to make the capacitance is the capacitance at the interface is the inverse of the capacitance of your charge pass region. I just make it again here. That's the semiconductor here, and you have the pass charge region here, and you can measure this capacitance with this kind of potentiostat combined with a lock-in. So you can plot, for example, 1/C2, what we call Mochotsky plot, what I present here. And you can have in your flat potential, and even you can have your doping. As you see here in this relationship, there is a doping here. You can get it from the slope. So all these electrochemical measurements are very important. And maybe if you want more detail, we can go ahead and do it. The last thing what I want to show you here is this setup, which is very important in order to get your spectral response of your semiconductor. You see here again, I put the 3 electrode. Here is the working electrode. Here is the counter electrode. And I just use as a reference electrode a carbon electrode. So in this kind of experiment, we don't need really the right reference electrode. So you have 2 carbon electrodes. One is counter and one reference. And then we can use a monochromator here, a chopper, and we can measure from one side half of the light coming to your electrode. We can measure it. We can measure the current, which is resulting from this excitation with the light, and the half of the light can be measured with a detector. And with this kind of setup, it's possible to measure only the photocurrent, which is coming from the light. And of course, this photocurrent, we have to know the origin. It depends on your electrolyte here, what you have. Okay. So this kind of experiment is very important. I will go back to this experiment. I use it very much. You can see this reference, which is from 1993. Here, how we can characterize the interface semiconductor electrolyte and how we can measure the quantum efficiency, for example, with this kind of setup. So another time, I will just focus on this kind of setup in order to understand better. And you see here that we use a box here, a black box, where you are sure that the light is coming from it's not the background light from the around, but it's only the light what you want to analyze. Okay. So of course, when you find your quantum efficiency, you can analyze it, and you know, for example, where you lost some current, etc., etc. So this is very important issue, but we will every time try to understand a little bit more. Now there is another setup where we call the rotating ring disk electrode, and this rotating ring disk electrode, it's 2 potentiostats here, not only 1, but 2 potentiostats, where you can, with this setup, know the oxidized current, the current resulting from an oxidation, we call it E, and the current resulting from a reduction, and you can measure both of them, and you can know, for example, if you oxidize water or you have a corrosion, etc., etc. So that's a very important setup. Last time I told you that I want to show you this kind of setup, and I will just stop here and give the floor to the student. So please keep in mind that every time you are doing your calculation, you have to think to ask yourself which experiment I have to do in order to reflect my result from the theory. It's very important that we have to make together what you are calculating and which setup you have to use to make to see if what you have found in theory you can see it in experiment, because experiment means technology. Thank you very much.
Thank you very much, Professor Ahmed Ennaoui, for this very useful introduction for the measurement for photoelectrochemical topics. Now, it's my pleasure to introduce the speaker, Dr. Jihad Labrousse. She is from the Laboratory of Condensed Matter and Interdisciplinary Physics. Her main topic, research topic on the 2D materials using density functional theory, ab initio calculation, and also molecular dynamic. Her study on 2D materials as for application of hydrogen storage. Today, he will speak of her obtained results for different 2D materials. You have the floor, Jihad Labrousse.
Thank you, Mr. Benyoussef. Before starting, please let me know if you cannot hear me for the rest of the presentation. You hear me right now, right?
Yeah, hear you.
First of all, let me thank Mr. Ennaoui and Mr. Salam for letting me here being with you today. And I would like also to thank Mr. Benyoussef for his guidance, his advices, his support, and for his invitation to be here with you today to present my work, which is new two-dimensional materials, computational design for hydrogen storage applications. As a plan of my work, I'm going to start talking about energy storage challenges, and I'll talk about the main methods of hydrogen storage. Then I'll give the main issue that we want to solve, and I'll present some results, and I'll finish by a conclusion and perspective. Well, actually, renewable energy sources are experiencing a period of rapid growth, with the U.S. Information Agency predicting that it will be the fast energy source in the near future. However, renewables suffer from supply and demand imbalances because the mass productive period is when electricity demand is lowest, and the vice versa, leading to the waste of energy. To solve this problem, the renewable must be complemented with other dispatchable energies that can immediately adjust their production to match with the variation of energy demand and hydrogen storage is a promising option to serve this dispatchable energy role. Once hydrogen is created through electrolysis, it can be used in stationary fuel cells, provide fuel for fuel cell vehicles, also injected into a natural gas pipeline to reduce the carbon intensity, stored as a compressed gas cryogenic liquid, or maybe as a wide variety of loosely bounded hydride compound for later use. We know that batteries are considered as a good material to be a tank for energy, but batteries unfortunately suffer from storage degradation because it can only store a limited amount of energy, where hydrogen fuel can be stored for a long period of time and in quantities only limited by the size of the storage facilities. Actually, according to Steve Sisayski, the director of business of Fuel Cell and Hydrogen Energy Association, he said that batteries takes 4 hours or less to discharge, while hydrogen can address a longer duration, needs days or even weeks. According to this whole things, we can conclude that hydrogen fuel is a promising fuel for hydrogen for renewable energy. But how we can store hydrogen? Actually, to store hydrogen, we need two methods: physical storage, and there is another method which is chemical storage. Let's start with the first one, which is physical storage. Actually, using this method, we can store hydrogen in gaseous form at high pressure, also in liquid form at 1 atmosphere pressure needed for like -252 degrees Celsius, which is the cryogenic temperature. Actually, the choice of the shell or liner that comes near to the hydrogen is important for every kind of reservoirs, because we can save hydrogen for the safety of people. And it is favored to use the steel because this kind of liner directly absorbs the mechanical stresses. And also there is another barrier for hydrogen called aluminum. Another method, which is chemical storage, we can use this method to store hydrogen in solid form. In this method, the hydrogen is chemically bounded with other elements. There are actually three categories. Chemical hydride, for example, there is ammonia boron. The second category, which is metal hydrides, there is sodium hydride, calcium hydride, magnesium hydride, in where the hydrogen is dissociated on the surface. After that, there is a diffusion in the metal, and the last step is formation of the hydride. There is another family called complex metallic hydrides, which are amides, borohydrides, alanates. These materials actually are considered as a good materials for hydrogen storage applications. The third category, which is sorption materials or sorbents. We have metal organic framework. We have also carbon-based materials. For example, there is carbon nanotubes, fullerene, porous carbon, and the improved graphene. I call it as an improved graphene because we all know that graphene is not a good material for hydrogen storage applications owing to its abundant energy. But we are going to improve the storage and transfer and electronic properties of this material to be a good material for hydrogen storage applications. So we are going to focus on carbon-based materials, as I said before. There is, as I say, carbon nanotubes. This material is considered a good material for hydrogen storage because it can absorb a lot of hydrogen molecules with a gravimetric capacity up to 3.0 5% by weight, and with decoration with some metals like titanium, scandium, aluminum, and vanadium, it can achieve a gravimetric capacity up to 9.8% by weight with decoration of scandium. Another material called fluorine considered also as a good material because it can achieve a gravimetric capacity without decoration up to 7.7% by weight, and with decoration of some metals, it can achieve a gravimetric capacity up to 9% by weight with a dissolution temperature up to 773 Kelvin. There is also porous carbon. This material can achieve a gravimetric capacity ranging between 3.99 to 5.05% by weight with a gravimetric capacity up to 77 Kelvin. Graphene, the last material, not considered actually as a good material for hydrogen storage, and that's what we're gonna solve in the rest of the presentation. Let me just talk a little bit about graphene. Graphene is a single layer of graphite that has been isolated from a thicker part or grown into a single layer. This material, the distance between two carbon atoms in this material up to 1.42 angstrom with an angle of 120 degrees, which means that our material has a hexagonal structure. This material have a lot of properties, for example, an excellent mechanical stiffness up to this value and an optical transparency more than 90%, and the charge carrying mobility ranging between these two values. This whole properties make it a good material to be used as a gas sensor, as an ultra high frequency transistor, as a potential electrode materials, but actually it cannot exceed a few, it cannot exceed the hydrogen storage barrier of a few percent by weight. The solutions for hydrogen storage applications, graphene can be used directly as basic material that takes part in sorption and desorption processes. Also, for desorption and desorption of graphene itself, assisted by additional catalysts, or maybe designing a compact structure with graphene sheets. Of course, our objective is propose a new two-dimensional materials as a tanks with a large theoretical storage capacity for hydrogen molecules. Before talking about the results, let me just talk about the technical system targets according to the Department of Energy to let hydrogen be stored on board for fuel cells vehicles. Well, actually, Department of Energy trying to reach 5.5% by weight as a gravimetric capacity, and also as a 40 gram per liter as a volumetric capacity, and the storage system costs $300 per kilogram in the near future. Well, as I said before, we are going to improve graphene to be a good material for hydrogen storage applications. So we have substituted two carbon atoms by boron, aluminum, and germanium. As you can see here, the geometry structure of this materials are similar to that of graphene. I just want you to know that we work it basically on the unit cell, but the results will be shown in supercell just to be able to see the carbon hexagon. After optimizing the lattice parameters of this material, we can see that for the whole materials, A equal to B equal to, ranging between 5.14 and 5.17, which is greater a little bit of the bound length of graphene, and such differences is because of the radius variation across these atoms. And of course, the angle was 120 degrees for the whole materials, which means that our material have a hexagonal structure. We studied further the stability of these systems by calculating the formation energy, and we found that our materials are stable, were stable owing to the negative value of formation energy. Well, actually, recently, Zenini all has succeeded in synthesizing a new diamond like PCX phases. And this is the scanning electron microscopy of BC3 sample. And the second image was, is BC4 phase. I just want to show you the scan electron microscopy of BC3 because we are going to work on this material. As I said before, we are going to test these materials to know the capacity of these materials for hydrogen storage applications. So we have placed our, in order to know the mass stable position and distance, we placed our hydrogen molecule on different position on the cell, on the top of carbon atom, on the bridge between two carbon atoms, on the hollow of carbon hexagon, also on the top of X atom, on the top between carbon and X atoms, and on the top of carbon and X hexagon. X was boron, aluminium, zinc, and germanium. And also the distance between two hydrogen atoms was not more than 0.74 Armstrong for the whole materials. Further, we calculated the absorption energy of these materials, and we found that for the whole materials, the absorption energies are ranging between minus 0.2 and minus 0.6, which is the suitable absorption energy for hydrogen storage applications according to the Department of Energy. We further calculated the density of charge of these materials. Well, the yellow and blue light colors indicates the loss and gain of charge, respectively. The negative charge between our substrate and molecule polarize the positive charge of the lower atom, which means that there is a polarization mechanism happening here. We observed while the absorption of the hydrogen molecule at the surface, the hydrogen is polarized with an electrical field on the surface. Therefore, between hydrogen molecule and our layer, there exists then a dipolar interaction, which means that our material and our substrate are connected by a van der Waals interactions, which is the physisorption or absorption. And this exchange of electrons was confirmed by Badal charge analysis. Well, we calculated also the diffusion path of this molecule on the surface, and we found that for the whole materials, the hydrogen molecule can easily mobile on the surface owing to the low activating energy. We have increased the number of hydrogen molecules on the cell, and we found that BC3 monolayer can absorb 11 hydrogen molecules with a gravimetric capacity up to 10.51% by weight. The second monolayer, which is LC3 monolayer, can absorb 16 hydrogen molecules with a gravimetric capacity up to 11.80% by weight. The third monolayer, which is NC3, can absorb 17 hydrogen molecule with a gravimetric capacity up to 9.73% by weight, and the last one can absorb 17 also hydrogen molecule with a gravimetric capacity up to 7.25% by weight. We calculated further the absorption energies of the increased numbers of hydrogen molecule, and we found that our material cannot absorb more than the previous numbers of hydrogen molecule because of the low value of the added hydrogen molecule of each of our in each of our substrates. We further calculated the desorption temperature of these materials, and we found that for the whole materials, the desorption temperature was close to 300 Kelvin, which is the ambient temperature, which means that our material can serve as a good material for reversible storage of hydrogen molecule. When I'm talking about reversible storage, I'm talking about relieving our molecule from the substrate at this desorption temperatures. For the rest of, further we calculated the density of states of these materials. We can see here that the whole materials keep it. They keep its behavior before and after absorption of hydrogen molecule. And also there is a shift towards the negative energies, which means that our materials are stable. And also there is a hybridization between hydrogen 1s states and carbon 2p states for the whole materials, except for the NC3 monolayer. There is another hybridization plus the first hybridization between hydrogen 1s states and zinc 3d states. Well, as a conclusion, we can conclude that according to this whole results, our material can be a promising materials for hydrogen storage application in this. In real life. And as a perspective, maybe we can use molecular dynamics for calculation for our materials, and maybe we are going to predict a new materials for hydrogen storage, and that's what we actually doing right now. Before finishing my presentation, I would like to thank once again Mr. Salem and Mr. Ennaoui, Mr. Benyoussef, Mr. Kins, my colleague team Khalid Al-Sfar and Mr. Mounkachi for being here for me today, and thank you.
Thank you very much, Dr. Jihad Labrousse, for this nice talk. Before I open the floor for question and comment, I ask Professor Ahmed Ennaoui to make a comment on Dr. Jihad Labrousse lecture. You have the floor, Professor Ahmed.
Yeah, thank you very much. Thank you, Dr. Jihad, for this nice talk, and very well explained the problematic when you are making your calculation. I think you have seen that if you have making a calculation and you don't make any experiment, it's a little bit it's half of the it's my opinion, of course, it's half of the cup which is filled, or therefore it's very important that the student try, maybe not during the PhD, because when you are doing a PhD, you want to be expert and specialize in one thing, and the lab were built by Professor Benyoussef, and now there are other professors, they are working now actively. They are very expert in theory. Now, one has to find some possibility to do experiment. Is very important.
Yeah,
Yes.
we need to do. I mean, we need to do the experiment studies for this material to know if really we can consider as a good material for hydrogen storage applications in the near future.
Yeah.
So we need to do
Yes.
experiment study.
Yeah. So one question regarding this link between theory and experiment is there are different banding when you are absorbing something. It can be chemisorption, it can be physique sorption, and there are three bonding: covalent, ionic, and van der Waals bonding. And
Yes.
are you able to distinguish or to calculate, for example, for a given material, which bonding is dominant in theory, and to see this with experiment? With experiment, is very possible to know covalent bonding, ionic bonding, van der Waals bonding, and something which is irreversible. This means you absorb something and then it will stay there because you form a stable material. Is there any work in the lab which is done in this direction? The question, of course, is addressed to you and also to Professor Benyoussef, because he know the thing since long time. So is there any possibility? Because for the technology, it's very important to know experimentally which, for example, density function theory or other, or advanced density function theory, when you try to add something, if you can really know or find that's what the theory is going to predict, you can find it in the experimentally in terms of this three banding, which one is dominant. Can someone also in the
Okay,
attendee, you
okay.
can also participate? Yes.
Okay, thank you for your question. First of all, I think we can know the van der Waals interaction and covalent interaction because of the density of states. Because when we do physics option, we talk about van der Waals interaction. I mean, when we put our hydrogen molecule on the surface, the nature of or the behavior of our material will never change after absorption of a hydrogen molecule according to the van der Waals interaction. But when there is a covalent interaction, maybe we are going to talk about exchange of electrons, and maybe it can change the nature of our material after absorption of hydrogen molecule. So I think this is how we can know the difference between covalent and the van der Waals interaction.
Okay, thank you, Jihad, for this answer, for this question, a pertinent question of Professor Ahmed Ennaoui. Of course, using density functional theory, it is possible to know the nature of bonding, covalent, polar, non-polar, or ionic bonding, and also van der Waals. And for the 2D material study by Dr. Jihad Labrousse, for the substrates bonding are essentially covalent, but for the adsorbed molecule, physical adsorption, the bonding is essentially van der Waals, because the distance is around 3 angstrom. And it is easy using density functional theory to know the nature of bonding, studying the and also and also charge distribution and distances. We can know the nature of bending. There is another, thank you, Professor Ahmed Ennaoui, for your comment. I open the floor for question and comment. I have already one question from Hassan Munir in the chat. He asked, quelle est la différence entre un matériau 2D et 3D pour le stockage d'hydrogène et quelles sont les propriétés physiques qui possèdent un matériau 2D pour avoir ce stockage d'hydrogène? I have the floor, Jihad, to give answer to Hassan Munir. Jihad, open
Yes, yes. The difference between two-dimensional materials and three-dimensional materials, I mean bulk, actually, I think of the quantity of pouring hydrogen molecule onto these materials, because we can use two-dimensional material for physisorption and chemisorption, and also for 3D materials we can use the both, but it is favorable to study to work on two-dimensional materials because it can absorb amounts of hydrogen molecule more than 3D materials. And yeah.
Thank you. Other question? I make a comment about the 2D and 3D dimension. Why 2D is very important for hydrogen storage is because the 2D material has a very high specific surface area.
Yes,
for example, with graphene, you have more than 3,000 square meter per gram. Then a very big storage surface because the hydrogen is stored on the surface, on the both sides of the material. And for this reason, it's very important to use 2D material. And as shown by Dr. Jihad Labrousse, for the material she show 2D material, some of them have 11 weight percent and very high compared to 3D material magnesium hydride. Are there some other questions for the speaker, Jihad Labrousse? Are there some questions? Or you can read your question in the chat.
I can ask or
No, you're waiting for answer.
Okay. Okay.
Are there questions? I have a question about the, you speak about the physical storage. Now it is the physical storage which is used in the industry and so on. Solid state storage is at the research level. Have you some idea about the evolution of the storage using solid state storage? Is it in the industry now or not yet?
I mean, for two-dimensional materials?
No, in general.
Actually, I don't have any. I don't have any idea about hydrogen storage on solid state in real, now.
I think for magnesium hydride, for three-dimensional magnesium hydride, there is some company for stationary storage, not for mobile storage, but for stationary storage, there is some company for magnesium hydride. You have other question from Shafiullah. Do you think that what is the possible solution for hydrogen transportation?
Where is the question?
Do you think what is the possible solution for hydrogen transportation?
When you talk about transport, we talk about diffusion, migration of the hydrogen molecule?
No, I don't think so. I think about hydrogen transportation in tanks. Is it possible to transport it as a liquid or as a gas or in solid state?
Well, people right now was working on a gaseous and liquid form for the transfer of hydrogen molecule, of hydrogen in general. But in chemical, using the second method, I think they use it with magnesium right now, as Mr. Benyoussef said. That's what I think.
Maybe for the transportation of hydrogen as which is stored in chemical hydrogen in H3 ammonia.
Ammonia boron.
Yeah, for the transportation of hydrogen, the pipeline.
Okay.
Are there some other questions? You didn't give more detail about graphene. Is it, what's the drawback of graphene as material for hydrogen storage?
Well, we all know that graphene not considered as a good material for hydrogen storage. We improved the electronic and transfer and the storage properties of this material by designing a compact structure with graphene sheets, as you see before in the presentation, by substituting 2 carbon atoms with the previous atoms in the presentation, which is boron, aluminum, and zinc and germanium, and there's more in the future. Yeah.
Drawback is the very low disruption temperature, is it?
Please, I cannot hear you.
The very low disruption temperature for graphene.
Yes. It has a low disruption temperature. I think is equal to like 50, 53 or 54.
Yeah.
Yeah, that's why we cannot use hydrogen molecule on this material, because the disruption temperature cannot be able to let hydrogen molecule release from the substrate, and either its bending energy is so low it cannot. We cannot put hydrogen molecule on this surface. Graphene.
Another question from Mbark Oussous. Quelle manifestation de la nature relativiste des fermions de Dirac sur les propriétés chimiques et physiques des matériaux 2D? Nous avons parlé.
Okay. Okay, you can answer. I don't know.
We have only the question for 2D material.
Okay.
Allez-y,
I
Jihad.
actually didn't study. I actually didn't study the fermion or fermion and the direct properties of this material. We just studied the electronic. I mean, transport. I mean, diffusion of this material on this of our molecule on the surface, the reversibility mechanism of this material to be a good material for hydrogen storage. But fermion and Dirac, sorry, I didn't study this side.
Pour Marc Oussous, qui a posé cette question de l'apport des matériaux 2D relativistes qu'avec le compte de Dirac. Le compte de Dirac, il donne beaucoup de propriétés intéressantes au graphène, hein, conductivité, etc. Alors, si on le passive par les atomes d'hydrogène, on ouvre le gap. Donc, l'aspect relativiste disparaît. De même, lorsqu'on absorbe des molécules d'hydrogène dessus, les interactions font que cet aspect relativiste disparaît. Et donc, l'absorption de l'hydrogène ou la passivation du graphène par l'hydrogène fait disparaître l'aspect relativiste et le compte de Dirac. Par contre, pour les matériaux étudiés par Dr Jihad Labrousse, sont des matériaux qui n'ont pas cet aspect, lorsqu'on met AlC3 par exemple, ou ZnC3, ce sont des semi-conducteurs. Le gap est ouvert, donc il n'y a pas de compte de Dirac dedans. Et donc pour cela, l'aspect relativiste disparaît dès qu'on fait la passivation ou qu'on fait l'absorption des molécules d'hydrogène sur la surface d'un matériau 2D. Alors, une autre question par Hassan Mounir. Si on arrive à stocker l'hydrogène par un matériau 2D, comment on va le libérer en cas de besoin?
Well, that's why we calculate, I mean, we studied the reversibility and for this for this material, and calculating the dissolvation temperature of these materials. Actually, we studied the reversibility of this material to know how we can release hydrogen from our material when we need it, of course. I mean, we studied the dissolvation temperature. That we want to find a dissolvation temperature that is close to 300 Kelvin, which is the ambient temperature, and I think we are close to 300 Kelvin, so we can consider it. We can consider our material as a good material for in the near future for hydrogen storage. So if you wanna release our hydrogen molecule, we need to heat the substrate in a temperature up to 300 Kelvin, I think, for releasing our molecule from the substrate. Am I right?
Thank you. Are there some other question for Jihad Labrousse? Are there some other question? Okay, the next talk next Friday, Friday 7 April, will be given by Zuhair Mansouri for material for lithium-ion battery. Okay, no other question? Thank you. Thank you, Dr. Jihad Labrousse, for your nice talk, and for this very nice discussion. And,
Thank you.
And see you all next week. Thank you.
Inshallah. Thank you.
Professor.
I just want to add something, if you allowed me.
Yeah.
We have some, in the next weeks, we will have to deal with some very interesting topic about soiling. So we will have a colleague from Italy. He will talk about the basic physics of soiling. And another colleague from California, the Greg Smistad, he will talk about the performance and or the advanced in simulation and mitigation of photovoltaic soiling. And then one colleague from Morocco also, he will talk about in the same direction, but about the photovoltaic sustainability. And then I'm in contact with Elias, Dr. Elias. He's Moroccan, but he's in the United States, in Oak Ridge, and he's in the lithium-ion battery. He will give a talk. So we have already, or we win already 4 talks in the future. So next week it will be a student from your laboratory, I guess, Professor Benyoussef.
Yeah.
And then, yes, and then followed by this 4 talks.
Okay.
But we would like to have more students to give talks, to be active. I think it's very important that students talk, communicate, bring their knowledge into public, into attendee. That's the way of learning by doing. So I hope students will continue to support and to talk. And don't forget that your talk will be registered and diffused, and maybe one day your talk will be seen by thousands of people over the world. So try to keep in mind this. Thank you.
Thank you very much, Professor Ennaoui, and see you all next week. Bye.
Okay. Thank you.